Hello, we're group 29 and we are going to be taking a look at induction. Induction is a inference rule and it's a type of problem that can often be very difficult. And we're going to take a look at what induction is and how we can make induction problems a bit easier for ourselves. So let's start off with what induction is. Induction is a new inference rule. So given p of 0 as our base case, we want to be able to show p of k plus 1. In this case, it would be p of 1. And then eventually we want to work towards being able to say, well, therefore, for all n, p of n is true as well. So using these line numbers above, if we use universal instantiation of line 1.2, we get that p of 0 implies p of 1. And because we have p of 1 from line 1.1, we can use modus ponens of lines 1.1 and 1.4 to get p of 1. And then we can repeat that process to get p of 2 and so forth. So what are the components of an inductive proof? We need to start with a problem definition, and we want to say let p of n, our general problem, equal some problem statement that we want to prove. In this case, we're using an induction problem from the fall of 2019 practice final. So then we have our introduction. I will show that p of n holds for ... and we state that we will demonstrate that p of n holds over the constraint that we're given. For this problem, that constraint is n is greater than or equal to 1. Next, we say, I go by induction. This is just standard language, just like when we state that we go by direct proof. Now we want to prove our base cases. We want to show that p of n holds for our base case, the first value given. After that, we can proceed to the inductive hypothesis and say, now assume that p of k is true for some arbitrary k. And again, with the ... we're going to state that p of k holds over the constraint. We suppose that p of k will be true, and we build off of this. For our inductive step, this is where we want to show or prove p of k plus 1. For induction, this can be accomplished by algebra or other methods, and our end result is that we've shown that p of k plus 1 is true. In our conclusion, we indicate that in our inductive step, we show that p of k implies p of k plus 1 by direct proof. Because we've shown that for all k, p of k implies p of k plus 1, and we have p of k by the inductive hypothesis, we can move forward to say for all n, p of n. Therefore, p of n holds for all n that meet the constraint by induction. And that's our closing line. So let's actually look at this problem in detail from the fall of 2019 final. So this is number 6 from the fall of 2019 final, and we're going to prove that the following summation is equal to its closed form for all n greater than or equal to 1. So for our problem statement, we say let p of n be that the sum from I equals 1 to n of I times I factorial is equal to n plus 1 whole factorial minus 1. Our introduction, I will show that p of n holds for all n greater than or equal to 1 by induction. Our base case is p of 1. The sum from 1 to 1 of I times I factorial is 1 times 1 factorial. That's equal to 2 minus 1, which is equal to 1 plus 1 factorial minus 1. Note that right here we do not immediately leap to the n plus 1 factorial minus 1. We have to work towards that in the end. Therefore, p of 1 holds. So we've shown that 1 equals 1. In our inductive hypothesis, we say, now suppose that p of k is true for some arbitrary k greater than or equal to 1. We move on to our inductive step. Therefore, by the inductive hypothesis, the sum from 1 to k of I times I factorial is k plus 1 whole factorial minus 1. We want to get the sum from 1 to k plus 1 of I times I factorial. So in order to get that, we need to add the k plus 1th term to each side of our expression in the IH. That term is k plus 1 multiplied by k plus 1 whole factorial. Adding that to both sides, we get sum from 1 to k of I times I factorial plus our k plus 1th term, and then that's equal to the right-hand side plus that k plus 1th term. So that's going to simplify to the sum from 1 to k plus 1 of I times I factorial, and then the right-hand side stays the same from this previous step here. Our inductive step continued. With further simplification, we can factor out and rearrange terms. We factor out a k plus 1 factorial, and we're left with k plus 1 factorial times 1 plus k plus 1, all of that minus 1. We can simplify that further to get k plus 1 factorial times k plus 2 minus 1. And then recall that k plus 1 factorial times k plus 2 will be k plus 2 factorial by the definition of factorial. So therefore, we have the sum from 1 to k plus 1 of I times I factorial is equal to k plus 2 factorial minus 1, which is k plus 1 whole factorial minus 1. And that is exactly p of k plus 1. So, in conclusion, p of n is true for all n greater than or equal to 1 by induction. Just a few quick pointers. We want to start by thinking about what we want to show. So in this case, we wanted our sum to k plus 1 to equal k plus 2 whole factorial minus 1. By the inductive hypothesis, we had our known fact for the sum from 1 to k, and we can use that fact to build upon. To transform our sum into the k plus 1 sum, we need to add the k plus 1 term to both sides. And once we've done this, we can use algebra and the definition of factorial to simplify, and our expression ends up matching p of k plus 1, which completes the proof. Also keep in mind that the inductive hypothesis does not provide you immediately with the k plus 1 sum, and that you have to work towards that. Otherwise, you risk getting into some circular reasoning. Thank you very much. I hope you enjoyed watching.